our own Vice Chancellor, Professor A.B. Pandit, who will be delivering lecture, late C.J. Bhumkar Memorial Lecture. I will not mention the topic immediately, I think it is already mentioned. Can I request Girish Nagarkar and Durgavale to escort today's speaker on the dais? Now may I request Dr. Girish Nagarkar to welcome today's speaker with a flower bouquet.
Thank you.
Sir, welcome. On our own premises, we are welcoming you. It's a really great pleasure. I think this is sixth year, I hope, where we are organizing this C.J. Bhumkar Memorial Lecture. We are sorry we are delayed by almost a month. It's because of pandemic situation we could not arrange, and we plan to have this lecture in physical mode. Last year we have organized this on virtual mode, both N.R. Kamath Memorial Lecture as well as this lecture also we have organized in virtual mode. But this year we specifically planned to have this lecture in physical mode, and that's why it was delayed by almost 20 days. It is supposed to be on 20th of March, but it is almost, now we are on 20th of April. So I, on behalf of the Color Society, we apologize for that. And now may I request Dr. Girish Nagarkar to present his welcome address.
Good evening, friends. On behalf of the Color Society Managing Committee, I welcome you all for the late Shri J. Bhumkar Memorial Lecture. My greetings to you all. Today's speaker, Vice Chancellor, ICT, Professor A.B. Pandit, Mrs. Priya Bhumkar, all respected members of the and a very hearty welcome to all the members and the industry colleagues. This is our first lecture in physical attendance since the pandemic. So we are all happy actually, and because we had been used to doing online meetings and lectures for about 2 years. So slowly we are coming out of it, and I am sure that this will give us more opportunities and more progress. I would like to say a few words about Mr. C.J. Bhumkar, and my experience is that we used to meet him as a supplier. During my Clarion days, we used to visit him and offer our special additives actually. And my boss from Clarion, Switzerland, Dr. Kras, whenever he used to come, he used to first ensure that we have made an appointment with Mr. Bhumkar. And that was always the first meeting during his visits. And always we used to visit him. And the motto of the meeting was not only to sell the product, but to get some knowledge, by meeting him. And we never failed in that. And so that is a good memory of meeting him. And so we in Clarion, actually we missed him a lot. And especially the meetings and very, very knowledgeable sharing from his side. Thank you very much, and I will hand over to the Vice President, Mr. Dapre. Can I request you to give a flower bouquet to Mrs. Priya Bhumkar? Thank you. May I request you to share your reviews? Yeah.
Good evening, everybody. Yeah. I can't tell you what a heartfelt pleasure it is to be amongst you all today to be back as a color society after a gap and to see the overwhelming amount of love, affection, and respect which everyone in the industry and particularly in the society has for my father-in-law. As you mentioned, Dr. Nagarkar, 20th March is the birthday of him, Mr. C.J. Bhumkar, and he would have turned 87 this year. But he passed away in 2009, so it's been almost 13 years that he's not with us, but it still seems like he's there with us all the time, every single day in our, I think, not only in our family, but in our company, Saujanya Color, and amongst all the people in the industry who are so near and dear to him. The world is changing very fast. We are all almost like caught up in like a typhoon, which is swirling around us and which is carrying us at a breakneck speed, and we are all just struggling to even keep our heads above the water in the midst of so much uncertainty and so much change with everything that is happening around us, whether it is global trade, whether it is war, whether it is COVID, whether it is technology. So much change. I think human beings are grappling with a tremendous amount of change at the moment. But I think, and I see that there is a lot of young people also, in the auditorium. Probably you may never have heard of Mr. Bhumkar, or you may not have even, of course, you may not have seen him at all. But I think the one learning and the one thing which we can still carry forward from the generation in which he lived, which actually didn't see so much change, there was a lot of stability around. I think the one thing, one takeaway for our generation, for the next generation, is the amount of focus that he had. Unwavering focus on excellence, unwavering focus on his subject. And with the focus, along with the focus, because today we are distracted all the time. Every minute we will check our phones with WhatsApp or something. I think that kind of dedication and that kind of focus. And along with that, no matter how much knowledge he had within him, his pursuit of just simply reading and discussions and knowledge, pursuit of knowledge, just for the sake of pursuit of knowledge, because he loved to learn. I think these are the two takeaways which I'd like to, talk about here today. And I think everyone who has seen him and interacted with him will vouch that this is indeed, this is exactly how he was. So that's what we can carry forward. And this kind of a focus and this kind of a learning and knowledge ability actually allows one to build a large mountain and body of work, almost like a monolith, in so many years. This kind of a pursuit of knowledge with a dedicated focus, on and pursuit of something in one subject. This allows you to build something which is very high, like a tall mountain. And this is the legacy which he has left behind, particularly for a family, for a lot of the people, young people who worked with him at that time. So our respects to Color Society for always making it a point to celebrate this day with so much heart and with so much, really, really value it. So thank you for that. And the subject of today, Dr. Pandit, I think is very close to Mr. Bhumkar's heart, because the entire business that he set up is in mixing and dispersion technology. So this is also something, so we couldn't be more honored to have you, sir, today, talking to us. Thank you very much.
Thank you, ma'am. It's really a great privilege for Color Society. Today, we have almost 6 past presidents who worked with Mr. C.J. Bhumkar during our Color Society tenure. So 6 are there. Generally, for even seminar, these many past presidents never to be present. But for this lecture, I think today 6 presidents of past presidents of Color Society are present. So that itself shows how much affection Color Society and Color Society presidents have with Mr. C.J. Bhumkar. Now, one of the person who's worked very closely with C.J. Bhumkar, I request him to come forward and share some memories of Shri C.J. Bhumkar. Mr. N.S. Pradhan, please.
Dignitaries on the dais, my dear friends, students of UDCT, very good evening to everybody. This is my, really I can tell that this is my proud privilege to talk about a person under whom I worked and my first boss in the life, none other than Mr. C.J. Bhumkar. As I told Priya madam that I will become a little nostalgic about it. But then I am not allowed to take more time to describe Mr. Bhumkar or to share the memories I shared with him during my tenure in Asian Paints. In fact, my treasure of adjectives is just insufficient to describe this towering personality in the paint industry wherein I spent about 5 decades. My first job was that of Asian Paints. I will not go into the academic and professional achievements of Mr. Bhumkar, but certainly I will love to share some very light moments I had experienced during my tenure in the Asian Paints and till now, till his demise, when I was in close touch with him. After leaving Asian Paints, I had joined polyurethane. So that time, Mr. Bhumkar was aware of my whereabouts, my progress, and has been always a guiding force for me. So once he invited me to his house to show my video clips about the grouting by polyurethane and anti-corrosive treatment. And on his giant screen in Pakadi, we spent about half an hour, and he gave me very good tips regarding polyurethane, and he praised me left, right, and center. For a moment, I feel I have become very great, but that was not the case, because he was a towering personality in front of me. What should I talk about Mr. Bhumkar? Besides his professional and academic achievements, I had studied his very close, or say, very good virtues of his personality. Very few people know that Mr. Bhumkar's handwriting was par excellent. He used to send the notes to his subordinates in such a beautiful handwriting. Even his signature, normally big people's signature and handwritings are very shabby, but his handwriting was very, very nice. I used to admire those notes. Really, I still remember them. I wish I should have preserved it. Once so happened, he was a strict disciplinarian, very good boss. At the same time, he saw that each and every subordinate progress in his life and get adequate knowledge of the pen technology. Couple of moments I can cite here. Once, when I was in Asian Paints, I was keeping the record of the outdoor exposures panels vis-a-vis weatherometer panels and trying to compare and showing him the records. He was very particular about the records, and he used to advise time and again about that. So when I went to show him the records, he was very happy. He said, Pradhan, very nice record. सगळं छान आहे हो, पण अक्षर जरा सुधारा. रोज 2 पानं लिहून काढा. That was his, I took it in the right way, because that was a good advice for me. Because person who himself had such a nice handwriting is advising me. And there are many, many memories, sweet memories I can share with him, not only in the Asian Paints, but during my tenure in the paint industry, 5 decades, I was in close touch with him. I used to regularly telephone him and keep him abreast about my progress. And he was monitoring it also time to time. I remember another incident. In 1991, when I published my first article in Paint India of my life, he was the first person to read it and call me and congratulate me. There are many other memories, but the time is short, so I conclude here. Thank you very much, dear President, for giving me this chance to share my memories about my beloved ex-boss. Thank you very much. Jai Hind, Jai Bharat.
नाही आता तरी सुधारला असेल. Thank you, Pradhan sir, for sharing great memories. I mean, this particular aspect of C.J. Bhumkar, that having very good handwriting, was known to many of us, because he used to be there in each and every program of the Color Society. But I can definitely mention that, because I worked with him for at least 3 years, and thereafter I was secretary, until I'm secretary for almost last 20 years now, and by now, out of which 10 years, he used to attend each and every program. And he used to, whenever he tries something, it was really attractive.
So his signature is really, we have framed it and put it in our office.
Okay.
It is really so beautiful.
Now today we have really apt lecture or apt topic for C.J. Bhumkar's interest, as Priya Madam has mentioned about. And in addition to this, I think, sir, I can mention one more thing. I should have added one more additional word, that cavitationally induced mixing and dispersion in paint industry or in color industry altogether. I think that would have been more apt, because the business of Saujanya Chemicals is in dispersion, and that is coloring specifically, so it would have been more apt for this. And the group of people are from surface coating industry or paint industry, so that would have been more appropriate. Printing ink, or I can say surface coating industry. And to listen that, we have people from even Indore. The president of International Paint Association, he is also there. And many people are from industry, they are present here today. So without spending any time, can I request Mr. Shivaji Durgavale to introduce formally today's speaker? Please, Durgavale, please.
Good evening, ladies and gentlemen. It is my great pleasure to introduce today's speaker, Professor A.B. Pandit. Professor A.B. Pandit was born on 17th December 1957 in Mumbai. He completed his secondary school examination in 1974. He earned his B.Tech chemical degree from Indian Institute of Technology, Banaras, Hindu University in 1980, and earned his PhD Tech degree from UDCT, now ICT, in 1984. From 1984 till 1990, he worked in the Department of Chemical Engineering, University of Cambridge, United Kingdom, as a research assistant, and then as a research associate with Professor J.F. Davidson, working in the area of bubble breakup and design of multiplex reactor. He developed many novel designs of gas liquid contactors, and also developed new impeller designs. Apart from returning to India in 1990, he joined ICT as a UGC research scientist B, and was subsequently promoted to scientist C. In 1996, he was instrumental in starting a major activity and program in the area of hydrodynamic cavitation for intensification of physical and chemical processing applications. He was successfully exploited the cavitation phenomena for a variety of operations such as crystallization, emulsification, nanoparticle synthesis, and process such as esterification, oxidation on an industrial scale. He has been an active industrial consultant for many large-size national and international companies. A unique creative approach of using fundamental knowledge coupled with simple, elegant experiments has resulted into novel cavitational reactors. Professor Pandit has authored over 418 research publications, 5 books, and over 12 chapters, and has 15 patents, and is on the editorial board of 5 international scientific journals. He has guided 51 PhD and 92 master's students so far. In addition to his research contribution, Professor Pandit has contributed to innovation in teaching at graduate and undergraduate levels, demonstration experiments for elaborating the physical principle of many chemical engineering operations. He is actively involved in working with committees in the area of harnessing solar energy and with the tribal population in extending the chemical engineering principles for drying of farm forest product and water disinfection for potable water. He is the president of an NGO named Land Research Institute dealing with the energy and town planning sector. Professor Pandit is currently Vice Chancellor of Institute of Chemical Technology, Mumbai. Prior to this, he has acted as a dean in his capacity of research consultancy and research mobilization and HR for over 9 years. He has been the coordinator of ICT DAE Center for Chemical Engineering Education and Research in its inspection in 2008. He has successfully guided and completed many international science collaboration with universities from France, Netherlands, and Australia. He is also on the project appraisal and evaluation of committees of the DST and UGC Government of India. He is currently serving as a member of the Board of Governors of the IIT Bombay. He has been an active industrial consultant to many national and international industries. Professor A.B. Pandit received many awards. Few of them are ISTE National Award for Outstanding Research in 1995, Professor R.A. Raja Diksha Best Teacher Award on 15 occasions in the past 20 years, Vasvik Award 1996, Fellow Maharashtra Academy of Science in 1997, IICHE Hardilia Award for Excellence in Basic Research in 2001, Distinguished Alumnus Awards, Institute of Technology, Banaras Hindu University 2004, Distinguished Alumnus Awards, UICT 2008, ANSA Best Teacher Award 2012, Vishwakarma Medal of Indian National Science Academy 2015, Indian Chemical Council Lifetime Achievement Award in 2021, Fellowship of Maharashtra Academy of Science 1997, Indian National Academy of Engineering 2006, Indian Academy of Science 2008, Indian National Science Academy 2009, National Academy of Science in India 2009, Fellow of the World Academy of Science 2015. So Professor A.B. Pandit will share his knowledge and experience on Cavitationally induced macro, micro, mixing and dispersion. So ladies and gentlemen, please welcome Professor A.B. Pandit.
I usually don't need a mic because people say that you want to find out where Professor Pandit's lecture is, you just walk along UDCT and you know where he's taking a lecture. So I'm that loud. And that also helps preventing people going off to sleep during the lecture. President Color Society, Professor Mahanwar, Shri Nagarkar, Mrs. Priya Bhumkar. I wanted to share a secret, and actually part of the secret was let out by Priya. This area which I am going to talk on, actually late Shri C.J. Bhumkar is the originator of this particular idea. In the late 90s, early 2000, I was visiting Professor Mohan Shenoy's room, and C.J. Bhumkar was sitting there, and I had started work in the area of cavitation, and Mohan called me in saying that here is an opportunity for you to use cavitation for some specific applications related to paint and dispersion. In fact, till that time, I was concentrating only on the chemical transformations, had not bothered about the physical effects of cavitation. And while discussing with him, I thought that the kind of phenomena which is occurring, this phenomena in principle can also be used for carrying out dispersion, emulsification, so on and so forth, because the physical forces which are developed during the process of cavitation are responsible for the breakage and dispersion. So I started working into it. Unfortunately, because of his death, we could not continue. In fact, we had decided to work together, and Saujanya Chemical was supposed to sponsor a project. Unfortunately, it did not materialize. But I still remember receiving a small note, as correctly pointed out, in beautiful handwriting with his beautiful signature. If I look, that note might still be there with me somewhere, where he had listed out that we would like to study these aspects of pigment dispersion, pigment deagglomeration, so on and so forth, and we were supposed to work in the area of cavitation. And I am going to talk about work which was not done for Saujanya Industries, but similar work which was initiated because of the discussion which I had with late Shri C.J. Bhumkar. So, I wanted to share this secret with you. Is the topic which I am talking about is essentially originating from his thought process and based on the discussion which I had in late 90s with him in Mohan Shenoy's room. So the topic, as I have chosen, macro, meso and micro mixing, essentially as correctly pointed out, and you all know, I need not emphasize the importance of mixing phenomena in paint industry. Even when you buy a paint, it is always advised that before application you stir it up, settled mass of the pigment, you need to disperse it, and you know a good painter will immediately know whether the consistency has been reached or not just by agitating it and by stirring it. So it's basically what you are carrying out is macro mixing. It's a broad mixing. Prior to that, micro and meso mixing has already been carried out. Deagglomeration has already been carried out, dispersion has already been carried out. But because of the smaller particle size, there exists a tendency for these particles to come together and agglomerate. And whenever they agglomerate, their settling velocity increases. Even though you have a very viscous medium, the settling does take place. So is there a possibility for us to combine this effect of grinding and mixing together while carrying out this preparation of paint or surface coating material? And this is what is going to be the topic of today's discussion, is to what extent cavitation is really responsible or cavitation can effectively be utilized for carrying out not only just the dispersion, but grinding and dispersion simultaneously. Right? This is what the whole ball game is. If you can reduce a unit operation in your entire manufacturing processes, then you are likely to have a significant saving in terms of the processing cost, the time, so on and so forth. So before I actually venture into it, it is necessary for me to explain it to you what exactly is the cavitation phenomena. So the topic includes the basic description of cavitation phenomena, the kind of effects which are seen as a result of cavitation phenomena, how cavitation gets generated, what are the different techniques which can be utilized for generation of cavitation, and how these techniques can be applied in paint and surface coating industries to get a quality of paint which is essentially well dispersed, well homogenized, ready for application. So basic concepts of energy delivery mechanism, cavitation in nature, concepts of cavitation phenomena as such, the physical transformations, microbial cell disruption, and I'll tell you how microbial cell disruption is related to that as well here, because many a times the paint industry also faces a problem of microbial growth during the storage. So during the treatment process itself, if these cells or microbes which are present in a, let's say, E. coli are rendered unviable by disrupting them, then you can also need not use disinfecting chemicals or need not use the chemicals which will prevent the microbial growth. Then some applications, brief description about lithotripsy, nanoparticle synthesis, and sonochemical reactors, the type of equipments which are available which can be used to carry out this dispersion cum grinding operation. If you look into the literature, you will find that this particular mechanism of dispersion and grinding is called as cavitational milling. So essentially very similar to milling operation which you carry out using a sand mill or a high pressure homogenizer, a high speed homogenizer. A similar mechanism can be utilized or comes into play when you are using a cavitation phenomena. And whenever you want to carry out a scale of operation which is really large, acoustic cavitation, that is the cavitation generated by using ultrasound, is not very easy to scale up. As a result of it, hydrodynamic cavitation is a substitute, and we will see some specific application also related to those. So mixing, of course, is a blending process, and it involves two types of mechanisms. First is a convective transport, that the material gets transported from one location to another location, and during that particular process itself, the agglomerated material gets dispersed, or it tends to lose the edges of it, and the size of that agglomerate goes on reducing as you keep on recirculating. You will also remember, when you have a settled mass at the base of a paint tin, one stirring is not sufficient. You keep on stirring it, and gradually mass gets lifted, it gets homogenized. So multiple circulations are required, and these multiple circulations effectively do two jobs. One is the convective mixing, that is the transport of it, and second is the turbulent dispersion, reduction in the size of an agglomerate and gradual decrease in the agglomerate to take it to the primary particle size from which the agglomerates are formed. So ideal mixing equipment, we should be in a position to tune it depending upon the nature, agglomerating nature of the material. Nanoparticles are extremely difficult to de-agglomerate, mainly because they carry surface charge, and the moment you leave it aside, they will come together and they will agglomerate. And the moment they agglomerate, the specific properties of nanomaterials are lost. As a result of which, you need to stabilize these dispersions. Otherwise, if you don't stabilize it, these will get into not nano dispersions, it will turn into micro dispersions, and then eventually it will lose all its property, surface coverage property, hiding property, so on and so forth. I need not elaborate, you people are experts in that area. So blending process is controlled by mean flow, that is a bulk motion, the way we generally stir it. It just describes it using a propeller or turbine, and if you try to understand what a propeller does and what a turbine does, propeller generates a flow, turbine also generates a flow, but turbine, in addition to the generation of flow, it creates a local turbulence. So the dispersion mechanism, attrition mechanism of the agglomerates is significantly better with turbine as compared to propeller. So propeller is used for pumping of the liquid, whereas the turbines are used for pumping as well as attrition or dispersion. And if you are able to, and you will find that many different shapes of the impellers are available in the market, and people will recommend you, depending upon what plays an important role, whether the convective mixing is important or dispersive mixing is important. Once you understand this, depending upon the physico-chemical properties of the medium, as well as the properties of the solid material which you are trying to disperse, you will be in a position to tune it. Right? Why don't we use a radial flow impeller in the case of a fan? Because we don't want to disperse the fan. Fan is supposed to create a flow. It just circulates the velocity, circulates the liquid, giving you the effect which it is expected to do. So the blending process is controlled by eddy diffusion, which is essentially a different way of describing that it creates a local turbulence, and that turbulence dissipates the eddies, dissipates the energy, and that energy is responsible for the attrition of the agglomerated mass. The vessel is divided into two regions, a region near the impeller consisting of impeller and outside the impeller zone. So if I just go back, near the impeller you have a significantly higher shear rate. Away from the impeller, turbulence is much less, as a result of which it just circulates it. And the job of an impeller essentially is to bring this particular liquid back into a zone where the turbulent dispersion occurs. So essentially, the more number of times you bring it into the turbulent dispersion zone, better dispersive mixing is going to occur. So there are various models which are used, and you will find that when you use different types of impellers, the total amount of energy which you use to rotate the impeller gets dissipated in different forms. Some energy is utilized for creating flow, some energy is utilized for carrying out dispersion, some energy is utilized for carrying out the grinding or a milling operation. So you have many techniques which are available, which have been experimented with in ICT as well, where you use laser Doppler velocimetry, and we try to understand what is the role or what is the mechanism of dispersion. And we did a very nice study. We took a 1 meter diameter tank and we put the same amount of energy. Total quantum of energy put in the system remains the same, but in one case we put that energy in the form of a flow. In another case, we put that energy only in the form of turbulence. And we came to a conclusion that turbulence alone is not sufficient. You require a combination of the two to get the best effect as far as mixing and dispersion is required. Of course, this can then be utilized using CFD. I'll give you some examples of that in due course of time. So broadly speaking, since energy has to be conserved, out of the total energy which you supply, 33% leaves the impeller zone as a mean kinetic energy to create a flow, 30% leaves the impeller zone as a turbulent kinetic energy, and 37% of the energy gets dissipated in the impeller zone itself. When you use a centrifugal pump, you would have studied it, that centrifugal pump has got a hydraulic efficiency of, let's say, 60%. What happens to that balance 40% of the energy? You are supplying electrical energy. Where does that energy go? That energy gets lost in the form of turbulence, and this turbulence then can effectively be utilized to carry out dispersion, because the local dispersion can be carried out not by flow but only by turbulence itself. In the case of a propeller, out of the total energy supplied, 50% leaves. So it clearly tells you that propeller is more efficient in generating, creating flows and less efficient in terms of creating turbulence. 16% impeller zone is left in the form of turbulent kinetic energy, and 34% is dissipated in the impeller zone. When you use acoustic cavitation, only 0.1% of the energy is utilized in creating flow, whereas 99.9% energy is dissipated in the form of turbulence. So if you want to carry out dispersion, we must dissipate energy by creating maximum turbulence. If you want to carry out bulk mixing, macro mixing, turbulence is not required, right? So if you want to carry out, let's say, a stirring of milk in your tea, turbulence is not required. Just simple stirring is sufficient enough for you to carry out that mixing. Whereas, if you want to essentially dissolve a sugar in it, and you have large particles in it, you need to create a turbulence so the particles get accreted, small particles provide additional interfacial area, surface area, and the dissolution takes place. If you have large crystal sizes, it will take longer time to dissolve. If you have a very fine crystals, it will dissolve very quickly. So if you can have a mechanism which creates flow as well as reduces the particle size, your process of dissolution and dispersion is going to be significantly enhanced. So let us move our attention to cavitation now. I want you to look at this small video clip. See, nature is the best teacher anyone can have. It has all the time in the world. It does not waste any resources, and that's why it has survived so long. As a result of which, there is a possibility for us to learn from nature and mimic nature. And what you see here is a creature called as a snapping shrimp. I'm sure people must have eaten shrimps like the shrimps which you get, very similar, but this is one specific variety. Now this shrimp uses a cavitation phenomena, and it uses the cavitation phenomena by following Bernoulli's principle. Shrimp doesn't know that it is following Bernoulli's principle. We know that it is following Bernoulli's principle. Right? And Bernoulli's principle tells me that the total energy has to be conserved. So if energy gets converted from potential energy to kinetic energy, potential energy must come down. So if I am able to have more energy in the form of a flow or kinetic energy, out of the total energy, potential energy must come down. And we all know two forms of energy, potential and kinetic, and potential energy is usually expressed in terms of pressure, and kinetic energy is expressed in terms of velocity. So if velocity increases, pressure must go down. If pressure increases, velocity must reduce, because that energy has to be conserved. So what this shrimp does, it creates an extremely high velocity jet. And you all know that as the velocity increases, the pressure goes down and liquid can start boiling at atmospheric pressure. If you go on reducing the pressure on water, water can be boiled at much lower temperatures. If you want to boil water at the top of Everest, you can boil water at 68 degrees centigrade because the pressure is low. Similarly, if I reduce the pressure and bring it to, let us say, 30 degrees centigrade, the surrounding temperature, boiling of water can occur at 30 degrees centigrade. Boiling of water can occur at 15 degrees centigrade, 20 degrees centigrade. All of that you use in your watering vacuum pumps. I'm sure many of you use it in the industry. And you cannot beat it, because the moment watering vacuum pump reaches a phenomena of cavitation, the water starts evaporating. You can't get vacuum lower than the vapor pressure of water at that particular temperature. If you want to increase the vacuum, the only choice which you have is lower the temperature of that particular water, which reduces the pressure, vapor pressure of it, and then only you will be able to get higher vacuum levels. So what happens in this particular case, it pushes the liquid, a jet of a liquid, at such a high velocities that it creates a vapor cavity, and that vapor cavity is thrown at the prey, and the collapse of the cavity creates conditions which are extreme. And I'll tell you about what sort of conditions are generated. It is like you are walking along a street and somebody throws an atom bomb and the atom bomb bursts next to your ear. You are going to get disoriented for some time. And that's exactly what this snapping shrimp does. It throws that cavity at the prey. The collapse of the cavity creates a condition where the prey is partially paralyzed or disoriented, and then this shrimp has all the time in the world to go and eat it in peace. So can we have such multiple cavities being generated at a specific n number of locations, and every collapse of this particular cavity can create a shock wave which carries out dispersion, which carries out deagglomeration, which carries out erosion? Indeed, it is possible. So, as I said, we need to replicate nature because nature, as I said, doesn't waste any resources. And if we want to carry out operation in a sustainable manner, then it is mandatory for us to also use techniques which are sustainable in nature. And I need not tell you, you look at the 16, 17 SDGs, Sustainability Development Goals of UN, you will find conservation of energy is one of the major requirements. And we create these cavitating conditions by two means, as is well known. First is called as ultrasonic bath, and I'm sure you have used this bath for cleaning purposes, for carrying out a quick dispersion, and all the jewelers or watch repairers will put your watch in ultrasonic cleaning bath and creates a cavitating condition, and how it cleans it, I'll tell you in a minute. So this particular phenomena of generating cavitation is called as acoustic cavitation because the sound wave consists of a pressure cycle, that is essentially increasing pressure and decreasing pressure, a compression cycle and a rarefaction cycle. During the rarefaction cycle, if the pressure reduces and becomes equal to the vapor pressure of the medium, a spontaneous cavity gets generated, and a subsequent compression cycle, that cavity is compressed and it collapses, it implodes, and implosion of a cavity generates a significant severe conditions of temperatures and pressures, and I'll tell you what sort of temperatures and pressure conditions are generated. Alternatively, as the shrimp is doing, we can use a hydrodynamic cavitation where you need to just increase the velocity by putting some sort of a mechanical constriction, an orifice plate or a valve. You just throttle the valve and you will be in a position to create cavitating conditions. And as the cavities which get generated travel along from low pressure region, they get into high pressure region and they collapse exactly the same way as in the case of acoustic cavitation. These are the conditions which are generated. It generates temperatures in the range of 5000 to 10,000 Kelvin. The surface temperature of sun is approximately 6800 Kelvin. So you can imagine the kind of conditions which are generated inside this collapsing cavity. N number of reactions, ionic reactions can take place, and if we are in a position to capture that, many a times if you have water vapor inside this particular cavity, water vapor dissociates beyond 3000 degrees centigrade into H and OH. OH being extremely strong oxidizing radicals can oxidize the pollutants, and H of course can reduce. So reduction oxidation reactions can be carried, redox reaction can also be carried out very easily. It also generates extremely high local pressures of the order of 1000 to 2000 atmosphere. So you can imagine every cavity is something like a micro reactor, and you can carry out these chemical transformations, and the conditions which are generated are responsible for you to carry out physical transformations. However, if the cavity collapses on the surface, it does not collapse uniformly, because on the side of the surface there is no allowance for the liquid flow to come. So cavity does not collapse symmetrically, but it collapses asymmetrically. Asymmetric collapse of the cavity generates a liquid jet pointed towards the surface, and this jet has a velocity 200 to 300 meters per second. It is like a jet cutting. Now you can imagine if a pigment particle is present in it and a cavity collapses on the pigment particle surface, it's going to rupture that particular particle, and as the particle size reduces, you have carried out the grinding. And if you couple it with convective transport, mixing, that is convective mixing as well as turbulent mixing can be combined in one go. So these are some of the case studies which will talk. Emulsion, right? So you have oil phase and a water phase. Expose it to cavitating condition. First, it creates larger droplets, and you all know what we call it as a coarse emulsion. And then coarse emulsion is subjected to maybe high pressure homogenizer or high speed homogenizer. High speed homogenizer, high pressure homogenizer are nothing but creating hydrodynamic cavitating conditions. You can also carry out that dispersion using ultrasonic horn, using acoustic cavitation. So as you continue to irradiate with ultrasound, the droplet size goes on reducing and you can create extremely fine nanoemulsions without any difficulty. You may be in a position to reduce the quantity of dispersant or quantity of stabilizers which you need to have a very stable nanoemulsion. I'll give you some examples in due course of time as well. These are some theoretical calculations, because at ICT I cannot be just doing applied research. I need to, whatever I am talking, I need to have a science behind it. I need to support it by science. So we carry out these operations, study it, and then we try to explain the phenomena using the basic science, which is called as a dynamics of the cavity. How the cavity grows, how it collapses, the collapse of the cavity generates what kind of pressures, what kind of temperatures, and if those temperatures and pressures are known to us, then we can target specific transformations which we want to carry out, whether it is physical transformation, chemical transformation, biological transformation, all the transformations, because any transformation requires either supply of energy or removal of energy. So energy transformation is an integral part of any transformation, as a result of which it is necessary for us to understand what sort of energy dissipation levels or energy addition levels are required to carry out a specific transformation. This again tells you how theory and experiments can match. You will never get an exact match because the model can never be a precise model. You have to have a model which is mathematically solvable, and whenever you have a model which is mathematically solvable, you always do certain compromises, certain assumptions, which results into correct trends, but not necessarily quantitative predictions. So the inference from this basic discussion is cavitation can be used for producing oil-water emulsions. Cavitation provides high turbulent energy dissipation rate, which disrupts the interface and aids the surface creation. Cavity dynamics in various liquids was related to the resulting droplet size. Try to understand that. Whenever you have a bubble or a drop, there is a surface energy. Interfacial tension multiplied by area. Surface tension multiplied by area. Surface tension units are newtons per meter. Area units are meter square. So the product of this is Newton meter, and Newton meter is nothing but energy, right? Force multiplied by distance. So that has to be conserved. So whatever energy which you are supplying needs to get dissipated for creating an additional area, and that additional area results in the form of a dispersion, emulsion, or gas dispersion. Microbial cell disruption. As I said to you, that if you want to create a paint which does not necessarily develop a fungus, you need to destroy that fungal microbes which are present in it. And you can carry that out while carrying out the dispersion or mixing phenomena itself. And the situation there is, imagine this is a model, you have a microbe, I have a cavity. The cavity should deliver sufficient energy to disrupt cell, that is the cell wall needs to be broken. Cell wall is nothing but a drop, because cell wall has a strength. So if you supply energy which is sufficient in quantity, the cell wall will break. Now you press here, nothing happens, but if you press, use the same force in the form of a needle, all the energy is concentrated in that particular needle and you can easily penetrate your skin. Just pressing it will not, but the same force, I use a needle, I can do that. What am I doing? The same energy, I am focusing it by reducing the distance over which that energy is distributed. So if energy dissipated by the cavity reaches the interface microbe, then if it is not sufficient, nothing will happen, microbes will just move from one location to another location. But if the energy is sufficient, the microbial wall can get disrupted. So this tells you the mechanism. This is a cavity which is oscillating. And why does it oscillate? Because it is experiencing changing pressure. If you have a balloon, imagine if you move the balloon from low pressure region to high pressure region, from high pressure region to low pressure region, Because there is a fluid inside that balloon, the balloon will keep on changing its size. Exactly, cavity contains some form of a vapor. So as it experiences different pressures, it will keep on oscillating. Now, every oscillation is experienced by that microbes, and during that you can calculate what is the pressure associated with these particular oscillations. It's like adiabatic compression which is taking place, right? You know all the physico-chemical properties of the system, and you can carry out or predict whether the cell can be disrupted or not. So we carried out this and we developed a mechanism or a model which tells us how the cells can be disrupted. Now this is extremely important because different cells have a different cell wall strength. Not all cells are of the same quality. Let me tell you a joke related to that. You all know that essentially in nature, survival of the fittest is a theory which is well accepted. And when friends sit together and start working together or start having a peg or a two, then everybody becomes very intelligent. Everybody wants to contribute. And there is a reason for that, is every drop of alcohol kills 50 million brain cells. Which cells are going to die first? The weakest, which are not functional. So the concentration of the functional cells increase, and that makes you more intelligent. Right? This is a mechanism. This is a finely studied mechanism. The same mechanism is equally valid here as well. So different cells have got different cell wall strength. So if you want to kill or if you want to disrupt a particular cell, then you need to generate that much of a pressure, and that will result into disruption of this cell. So you can use all these models, and essentially what resulted into some sort of an equation or expression. If you look at this particular expression, those who haven't forgotten Arrhenius equation, you will find that the nature of this particular expression is very similar to an Arrhenius equation. You have an activation energy which is equal, needs to be overcome, which is the cell wall strength which needs to be overcome before the cell can be disrupted. So the same mechanism has been utilized out here. We carry out actual experiments doing that, and you will find that different types of cells can be fitted into and can be collapsed into the same model. Same model which also allows me to estimate what is the cell wall strength. Otherwise, very sophisticated instruments are required to assess the cell wall strength. Here, but this is going to be a destructive test where the microbes are being destroyed, but I will get an information what sort of conditions are required for the disruption of the cells. And even in case of a coronavirus, unfortunately, we did not have a biosafety lab of level 3. Otherwise, we were planning to carry it out. But I'm sure people, you might have studied on, I've got news on WhatsApp that you have got this ultrasonic device which is mounted in the corner of a room. It creates ultrasonic waves and it destroys the coronavirus. Mechanism is exactly the same as what I am just describing here. This tells you how the cell wall strength changes, and this again you can use it for water disinfection. So if you are going to use a water-based emulsion paints and you want to disinfect water so that eventually it doesn't result into a fungal formation, you can treat this particular water using cavitation and use this water where you will not have to have any antifungal agents added to it. Similarly, in a biotechnology area, every cell has got multiple enzymes in it. There are enzymes which are in the outer wall of the cell, and there are enzymes in the inner part of the cell, which is essentially the nucleus. The nucleus is inside. To access that particular enzyme, you need to disrupt the cell completely, and that requires huge amount of energy. But it is possible for us to tune the cavitation phenomena in such a way that you first recover only the, out of the total intracellular enzyme, only the enzymes which are peripheral enzyme, and then the enzymes which are in the cytoplasmic, periplasmic enzyme and cytoplasmic enzymes. You can carry out this by tuning the cavitation. right? And it can result into a significant saving. So I will also tell you about what sort of savings are possible if you adopt cavitation phenomena for dispersion of the pigments in due course of time. Mechanism remains exactly the same. You can have a huge savings, and this is now patented and now is being utilized for the recovery of intracellular products in the pharmaceutical industry. This is, I think, known to you. When you have a kidney stone, they do ultrasonic treatment, and this is the mechanism by which the kidney stone is disrupted. You can see what is happening is multiple cavities are collapsing asymmetrically on this particular big kidney stone, and it's sort of eroding it. When the size becomes sufficiently small, it can pass through urinary tract, and you don't have to go for operation. Alternatively, see, you can use a big hammer and break it, or you can use multiple small taps. So what they say is, "So sonar ki, ek lohar ki." You can use sonar to just chip away, or you can use one lohar, it completely breaks it with a single shot. This is like a pressure wave which is generated during the collapse of the cavity. Now, is this mechanism any different than what we carry out in the case of dispersion of pigments? It's exactly the same, and I'll tell you and I'll show you how it can be done. So cavitation can be utilized. It is a non-invasive method. Biodegradable particles can possibly be injected into tissues. In fact, cavitation has been also utilized for the treatment of cancerous cells, and this can be utilized for killing the cancerous cells which are actually present inside the body without operating it. You essentially just kill the cells at their location itself. And once the cells are rendered unviable, body takes care of it. It comes into blood, kidney filters it out, and effectively you can treat your cancer as well. You can carry out nanoparticles using hydrodynamic cavitation, as I said. Objective is what? Create multiple such locations of cavitating conditions, have n number of cavities, very similar to the concept which I used, the Sau sonarchy. Essentially have millions and billions of cavities, and each cavity has a capability of creating a nanoparticle. And using this, again, the particles which you are trying to carry out may have different nature. Some particles may be rigid, some particles may be ductile. If you want to reduce the particle which is ductile in nature, how do you do it? If you just use a hammer, if you want to break the rubber particles, then by just hammering it is not going to happen. Your hammer will keep on bouncing it off. But if you use a hammer with a point and apply the same force, it will keep on chipping away. So here also, imagine if I create a cavitating condition for a rigid particle is going to break as indicated by creation of a jet with higher velocities, 200 to 300 meters per second, which is equivalent to jet cutting which occurs. Alternatively, if I have a ductile particle and if the particle is in the vicinity of an oscillating cavity, then you will find that this particular material is stretched, release. So if you keep on taking this rubber and keep on stretching it, after some time that rubber is eventually going to break. And that's exactly what happens in this particular case. The frequency of oscillation is in sometimes megahertz region. So it is very fast oscillations which are taking place, which are responsible for the breakage of the particle. Breaks into multiple particles and the same situation continues. These are the particles of polystyrene divinyl benzene particles generated using cavitating conditions. You see how beautifully spherical these particles are. And when we created these nanoparticles, 20 nanometer diameter, almost for 2 years they remained completely stable because large surface area, surface charge, similar surface charge, it prevented the agglomeration and we could use it. This is essentially used as an additive into a drilling fluid used for oil well drilling. Right? Essentially it is used to give a ductility to cement. So if I use these mixtures in cement, the cement reduces its rigidity and it gives some sort of a flexibility. Because cement usually has a very poor flexibility, very similar to glass. But if you add this, then it gives some sort of a ductility to the cement. It improves the utilization potential. So cavitation has been successfully applied for producing nanoparticles. Hydrodynamic cavitation is energy efficient than acoustic cavitation. This is true only for specific applications. So pigment grinding. Renowned dyes and pigment manufacturing company was using a ball mill for pigment grinding to reduce the particle size from 0.66 microns to 0.53 microns. And you all know that initial reduction in the size is much easy, but to reduce it from fine size to finer size uses significantly higher amount of energy. So this resulted into high manufacturing cost of the respective pigment due to huge power consumption using ball mill. So what we did, we compared it, and you have a feed and ball mill, it took 144 hours. 9 passes were required to get the quality of the pigment in terms of its size distribution. Mean size was obtained 0.53. Same was carried out using hydrodynamic cavitation in 59 hours. 20 passes were required, same particle size, but you see the amount of energy consumption. We can reduce the cost from 40,000 rupees per liter to 16,000 rupees, almost one-third the cost. I am not saying that this is universally applicable, because every pigment, as you will understand, will have a different hardness. So you will have to create cavitating conditions which is sufficient to overcome that hardness. But in principle, as a proof of concept, it is indeed possible for you to adopt these techniques of cavitation. Carbon nanotubes. Again, dispersion of carbon nanotubes is extremely difficult. Right? All those who work in composites will find that the major energy goes in terms of dispersion of carbon nanotubes. Now you can use laser-induced cavitation here. Now, carbon nanotubes have got a property of absorbing light. It acts like a lens and concentrates it. Also, carbon nanotubes are extremely hydrophobic in nature. So there is a thin layer of air molecules attached to the carbon nanotube. Now, if you focus a laser on carbon nanotube, the energy associated with the laser is absorbed by the carbon nanotube. Its temperature increases, and as the temperature increases, the expansion of air takes place. It produces a bubble, and you suddenly stop that particular laser irradiation, that bubble will collapse like a cavity. Collapse of the cavity will be associated with a shock wave, as I have already discussed, and it will disperse the carbon nanotubes. We did this work in conjunction, in collaboration with TIFR, and we successfully published this work, which clearly showed on irradiation of femtosecond laser how the cavities were able to, not the cavities, but carbon nanotubes were able to absorb light, increase its temperature, increase the diameter, and the moment laser stopped, this will collapse, and the collapse of the cavity will result into a dispersion of carbon nanotubes. Same phenomena can be utilized. So, there are acoustic cavitation, there is laser-induced cavitation, there is hydrodynamic cavitation. Depending upon the application which you have an application in mind, you can use this cavitation phenomena generated by different mechanisms. These are the different types of equipments which can be utilized. Maybe another 5 minutes and I'll stop. This you all know that these are the equipments which are known to you. Right? These are different equipments which have been developed in ICT, have been designed and developed in ICT, and these are typically industrially applicable equipments where you keep on circulating the liquid. Why do you need to circulate the liquid? Because the cavitation as such does not have the capability of creating convective mixing. For convective mixing, you need to use a pump, but to carry out a dispersive mixing, you can use cavitation phenomena. So you have this acoustic cavitation, keep on circulating the material, and the dispersion continues, and you can get a very nice product, the product having the specific properties or specifications which you have. You need not carry out experiments. You can also carry out numerical experiments, which are much cheaper, but for that you need to first understand the fundamental principles, right? Otherwise it is GI-GO, garbage in, garbage out. You need to understand what inputs you are giving. Only when you understand physical significance and physics of that particular phenomena, you would be in a position to utilize it. So you carry that out, and this is a typical modeling of an acoustic horn, which you use, the cleaning horn which you use for cell disruption or for dispersion as well. You can resolve this and you can see how the jet gets generated, and this creates convective, but the velocities here are of the order of 50 centimeters per second, unlike 200 or 300 meters per second, which is occurring due to cavitation phenomena. It also generates a pressure wave. These are the predictions, and we have actually measured it. It creates a pressure wave. As I said, that transmission of a sound wave consists of compression cycle and a rarefaction cycle, and you can see how this entire pressure field is generated. Now this is responsible for those oscillating cavities. So if you are creating a varying pressure field, the cavity will oscillate exactly the same way. In some cases, the cavity will collapse, and the collapse of the cavity will result into the type of effect which you want. This is again the prediction of the same. You can carry out the CFD in case of hydrodynamic cavitation. Since the objective essentially is to create a mechanical obstruction, you can create mechanical obstructions in different shapes, and the shapes are responsible for creating and changing the number of cavities. The moment you change the perimeter to cross-sectional area ratio, higher the perimeter, shear rates are very high, so cavitation will occur at the edges of it. So if you can create more edges, rather than using a circular orifice which has got the least perimeter as against a rectangle or a square or number of squares, you will be in a position to maximize the cavitational events. The more cavitational events, more dispersion is likely to take place. And you can carry out this. This is the only equation which we have played around with. This is a second order ordinary differential equation. As a chemical engineer, I cannot end my talk without having at least one equation on the board. So this is a second order ordinary differential equation. It does not have an analytical solution. It needs to be solved numerically. And this numerical solution, since it is second order, it offers multiple solutions, out of which solution is correct. For that, you need to carry out experiments and validate your solution scheme. So you can carry out, since it is turbulent, cavity may choose different paths, and since the paths are different, the pressure versus time variation experienced by the cavity is also different. So the dynamics of the cavity, the way cavity behaves, is also different. Every behavior of the cavity is responsible for different pressures, for different temperatures, and then you need to be in a position to tune it, to control it. Only when you solve this equation, you know what parameters are required for you to tune it. If you are in a position to tune it, you can carry out cavitationally induced transformation using energies which are order of magnitude less than the energies which you would use otherwise. Right? These are the different hydrodynamic cavitation mechanical obstructions which have been used. Shows the pathways. So the key issues, as cavity is moving out of the liquid jet, sense a sudden change in the pressure and they collapse. Perimeter of the holes dictate the probability of cavity to cross over to liquid jet. Hole spacing should be large enough to maintain individual jets instead of coalescing liquid jets. Now these are our observations based on numerical simulations. So they are broad rules of thumb in terms of how you can go ahead and design a cavitational reactor. So in summary, mixing is brought about by convective, dispersive and diffusive mechanisms. It is possible to tune the energy delivery mechanism to achieve specific mode of mixing. Cavitation preferentially dissipates energy in the form of turbulence. Conventional reactors in combination with cavitational reactors, ultrasonic and hydrodynamic, can be tailored to improve the energy efficiency of blending and mixing operation. I would like to thank here, and this is the cavitational tree. There have been people who have been working underground, which is the fundamentals of cavities, where you understand the dynamics of the cavity, the nucleation model, the radical chemistry, mass, heat and mass transfer, flow dynamics, so on and so forth. And these outputs of these roots are fed to the tree above, which results into its application. And the application is increase in the transport, generation of free radicals, extreme pressures and temperature conditions, increase in the interfacial area, sonocrystallization, leaching, nanoparticle synthesis, emulsification, atomization, microbial cell disruptions. So this all has been explored since 1992. 1992 was my first paper in the world on hydrodynamic cavitation, and since 1992, 2002, 30 years now, more than 2,000 papers have been published in this particular area. I would just like to thank you all for listening to me very patiently, and I'll be more than happy to answer any questions which you may have. Thank you. Yes, please.
The question is there a particular size of a lot that can be treated in this way? Or in a sense, is there like a vessel size? It's a liquid or
Since you are,
because it's a sonic thing, right?
no, if you are going to use sonic, then you require multiple horns, because every horn has a certain zone of influence.
We tried sonic for dispersion
Yeah.
in our company, but we found it fairly ineffective.
So that's what I'm saying. So if you
Found
use,
it for the batch sizes that we have.
no, but what in that case you need to do is you couple it with a convective mixing. You put an agitator and then ensure that all your liquid is passing through that cavitating zone, which is only in the vicinity of the tip of the horn. So many people do it in such a way that they use multiple transducers. Every transducer has got a certain zone of influence, and you locate your transducers in such a way that the entire reactor gets covered. I think it is like this. In olden days, when you wanted to buy a music system and your room was very big, then what you would do is you would buy a huge speaker, 500 PMPO or 2000 PMPO, and the person who was sitting next to the speaker would get deaf. But you don't see it those days. Now you see, go to Bose, you'll find that small speakers strategically located, bringing about the same effect of musical experience. What you have done in the process, you have reduced the power consumption and still given you exactly the same effect. Similarly, if you use cavitation and use transducers strategically located in such a way that you will be in a position to get the same effect. Still, I would say that acoustically generated cavitation is still very expensive, because every transducer costs you a bomb, and having multiple transducer in one reactor is not at all economically viable. I would suggest that you should think in terms of hydrodynamic cavitation. What you require a vessel, you require a pump. At the most, you can use not a centrifugal pump, your viscosities are high, you can use a gear pump or a screw pump, and then keep on circulating it through a cavitating zone, which is essentially an orifice or a venturi or something like that, and keep on recirculating it. Energy consumption will be very low, and the liquid jet which is impinging, it is also carrying out a convective mixing. So every pass reduces the particle size. You can keep on recirculating it till you get the desired particle size distribution. Hydrodynamic cavitation in such application is much more effective as compared to acoustic cavitation. Thank you.
Any other question?
Thank you.
Thank you. Now, may I request Mr. Jaisal Parekh? Is that around? Okay. There is an announcement from IPCA that there is a conference. It's not that? Okay. Pulakar would like to announce something. Please.
I will take your only 1 minute time. Just I want to announce that as per last year, December end we are having one big seminar in Indore that we call Kumbh Mela. Kumbh. So all the sadhus I request to attend. First year artist will be Pankaj Udas, and we will have a lot of fun, and the New Year celebration will be there. Thank you very much. Again, I request all sadhus and sadhvis also to come. Thank you very much.
Thank you, Harish. Mukund. Now, Mr. Harish Agrawal, he would like to make announcement for tomorrow's program, I hope. Harish? He's not there. Okay.
You can announce it.
Tomorrow there is a conference come inauguration of new association that is called Surface Coating Society, or I think Society of Surface Coating. And it's a whole day program. I hope Dr. Samant is also one of the speakers for tomorrow's program. And Professor Pandit is...
I'm not going to give a big speech.
Yeah, he's going to inaugurate tomorrow. I hope it is at 10 o'clock. The inauguration is at 11 o'clock. And this is a complete a day program tomorrow in the same place, same auditorium. So I think you can attend that program, tomorrow program. Now we are at the end of this evening, and it's my privilege to perform a particular activity which is supposed to be. And it's a really privilege because today we really had very good speaker related to the paint industry, and I hope we definitely must be carrying good things with us. And I think we and Ben Giri can share this experience. We decided to go and meet Professor Pandit in his office, and in the afternoon we went to him, and I asked him, sir, there is a lecture which we are organizing, and we thought of inviting you as a speaker. Without any thought, he said, okay, why not? But then, what should be the topic? I said, the topic must be from your own field. And that's what immediately, I think within fraction of a second, this topic was been decided. We were supposed to ask him to send the topic title, and then we will print all these things. But I think we could complete that activity of getting the topic, title, topic, and everything within fraction of a second. And I think within a minute time, we were out of his office. And so quickly he has accepted our invitation for delivering this nice lecture. So, yes, of course.
Of course, C.J. Bhumkar. When I was C.J. Bhumkar memorial lecture, I immediately said, I still remember my interaction with him. I said, given an opportunity, definitely I would like to pay my tribute to him.
So, having shown this kind of affection, I would like to request the President, Colonel Soldier, Dr. Girish Nagarkar, to present a memento to Professor E.P. Pandit. Sir, Colonel Soldier would be happy to associate with you for a long time. And once again, I thank you, thank Professor Pandit for accepting our invitation. And now I thank all of you for coming here, attending this beautiful lecture. And I hope again tomorrow you can attend tomorrow's program. There will be many programs which will be organized by Color Society. Thank you very much and good evening.